Okay, our next talk is given by Alexei Colin, who's a computer scientist working in the Arlington office. And his talk is titled Glutx, a Betavoltaic transmitter for continuous glucose monitors. So, Alexei.
Thank you, Craig. So I'm going to present to you the medical device that me and my intern Kirthi built as part of the casting project. The goal of this device is to make life a little bit easier for diabetics patients. So patients with severe diabetes have to wear a continuous glucose monitor in order to track their blood glucose level all the time, continuously. Today's CGMs, these systems, are composed of three main parts. So that's a small sensor that goes under the skin, a transmitter that is worn on the body and connects to the sensor and broadcasts the glucose measurements over radio waves. And the third part is the receiver, which displays the measurements. And we will focus entirely on the transmitter part. This is what a transmitter looks like from a commercial device you can buy today. Our main focus is going to be on how the transmitter is powered. Today, it's powered by either disposable or rechargeable batteries, both of which create burdens for the patient. So if the battery is rechargeable, then you have to take the transmitter off your body, go put it in this portable charger, charge it for a few hours, right, and only then restore it on the body. If the device is using a battery that's disposable, then it will last about 6 months, at which point you need to toss the device. There's no replacing batteries. So we argue that batteries are not chemical batteries are not the only way to power such electronic devices. And we propose a transmitter that's powered by a beta-voltaic source that can last more than 10 years. So this beta-voltaic source is illustrated on the right. It's a device that can extract energy emitted by a mildly radioactive isotope of hydrogen called tritium that emits beta rays that land on a semiconductor material and thereby generate current. It's a principle very similar to a solar cell, except in a solar cell, the source of photons is external. Here, everything is built into a metal can, and it's a self-contained power source. So how does it compare in terms of lifetime to a chemical battery? So a chemical battery is very hard to tell, like how long will it really last. And I'm not talking about storage capacity itself, but just the robustness of the chemical process. If you leave a battery on the shelf for 10 years and come back and later plug it into some device, chances are that battery is not going to work, even if you technically didn't use any energy from it. We've all seen these leaked batteries with nasty white stuff in old toys or remote controls, right? So there's also this risk of chemistry going badly, and rechargeable batteries can catch on fire when it's too hot. There's been cases like that. In contrast, a tritium beta-voltaic is very robust. It's a very simple device, and it can withstand high and low temperatures. Great, so why can't we just swap out a chemical battery in our device for a beta-voltaic? Well, we cannot, because these two power sources have very different electrical properties. Namely, a beta-voltaic generates a comparatively low voltage and orders of magnitude less current. So why does this power characteristic cause problems for our glucose monitoring device, which you see illustrated here, right? So the device has the source on the left. That's a beta-voltaic cell that produces about 100 nanowatts of energy, right? Very, very small amount of energy over time. And on the right, you have the load that you want to power to do useful work, like deliver glucose measurements. So that's the sensor and the radio. And together, even with lowest power parts on the market, they take more than 15 or so milliwatts of energy. So we have no hope of just connecting the source to the load directly and powering it that way. But what we can do is we can power the load periodically, right? We can accumulate the energy into a storage element over a long time and then briefly power the load, right? And do this over and over again. So the challenge is then to build an electronic circuit that can manage this flow of energy as I just described. And of course, the secondary challenge is we want to make this load as energy efficient as possible and do useful work on just microjoules of energy. So why is it difficult to build such a circuit that does this energy management? Recall, the goal is to take the energy from the source, put it in the capacitor, and then eventually extract it from the capacitor and bring it to the load. To do that, you need to do three things. You need to keep the load off while you're charging. You need to turn the load on when you're done charging, turn it off when you're depleted your energy, and you might also need to convert voltage from low voltage to high voltage required by the load. And you can recruit an undergraduate EE student and ask them to build this circuit, and they will come back to you with the perfect circuit. It's going to use some high-side switches, some comparators, some voltage references, maybe a DC-DC booster, and it's going to work for some sources, but it will not work for our Betavoltaic. And the reason is because all these components, they consume more energy than is being at all produced by this very weak Betavoltaic source. So how do we deal with this? Well, we built a circuit that does the same thing, but very differently, right? So what it does is, again, if you look at that timeline illustrated, that shows how the device operates under the circuit that we're building, right? It plots the energy over time that's accumulated in the storage capacitor. So we started at empty, we charge up to some threshold, then we turn on, therefore start using the energy, so it goes down, and this repeats every cycle. So the reason our circuit can work from a Betavoltaic is because the way we do these three tasks is completely different. We do not use a voltage reference on the charge path. We use a very different way to convert voltage called Mark's voltage multiplier. We use a latch in our switch, which is essential. So basically, it's a combination of techniques that's allows us to charge from even a 20 nanoamp power source. So okay, so we designed the circuit, we prototyped it on the breadboard first, then we built this PCB board that's a more useful prototype of it. It is big because it's a debug version. But the question is, are you done after you've designed and built it? And I argue that no, because you need to figure out the values for some parameters. And I will just give you briefly a sense for what that involves. And that involves some modeling and some mathematical insight, which we spent some time developing. So the two parameters that you have to set are the voltage to which you charge and how big is your capacitor. And to illustrate it, you can see again this chart of how the device operates over time, how it accumulates energy, right? So if you start with this baseline, you're going to charge to some level and then discharge to some low threshold and so on. So what if I actually decrease the voltage threshold to which you charge? Well, then you will need to charge to a lower threshold, right? But then also discharge further down, because to support the same load, you will need to discharge to a lower voltage. Okay, fine. What if I increase the capacitor? Well, then you will charge to the same the same voltage level, and you will discharge less far down because you have more energy per voltage stored. Great, so which one should you do in order to operate efficiently? Well, that depends on power transfer from the cell to the capacitor, and that's not a constant function, and that depends on the current voltage. So we had to model it, and we built a numerical model. So here you see a plot of power over time. That's a different time axis from the ones below, from the ones above. And if you focus on the yellow regions, which highlight when you charge, when the device is accumulating energy, you see that when the device is accumulating energy, the power is not actually always maximum, right? So that means you're not transferring power at the most efficient rate. So what should you actually do? Well, the right answer is you need to do both. You need to lower the voltage, the turn-on threshold a little bit, but also increase the capacitor a little bit. And thereby, you basically create this band and operate at the maximum power point. Great, so that's a lot of tails, but does it actually work? So we did build an experimental setup to test this. So here you see it's sketched out and photographed. So there's this prototype right in the middle. that's connected to a real commercial underskin sensor that's submerged into a synthetic solution that's a substitute for blood. And this prototype is broadcasting Bluetooth packets that we then see on our laptop. So does it generate any glucose readings? And here's a plot of glucose readings over time for 3 separate experiments, where each I made the solution to be to have a different concentration of glucose in it. So you can see that the sensor is indeed detecting the levels, and we get the radio packets reporting those levels. Cool, so how long does it take to get one sample, or in other words, one transmission? Well, it takes us about 45 minutes on average just to charge for one sample. And that's, of course, a lot, but that can be improved by much more efficient software. Right now, software is doing a lot of wasted work that we can't easily get rid of. So I believe this can be sliced to about maybe 30 minutes per sample, where, of course, the commercial meters that commercial glucose meters that operate on a battery, they can deliver you a sample every 5 minutes, right? To do that, we would need to have a bigger power source, a bigger cell, or a more efficient photovoltaic cell, betavoltaic cell, which are actually being developed. So there's hope. There's hope. It's not perfect, but we've proved that we can actually charge from such a weak source, which is really the challenge here. And we've also estimated the efficiency of this power system by measuring the power that's delivered by the cell and the power that actually ends up, the energy that ends up in the capacitor. And we've seen that the ratio between those two is about 88%, which is frankly higher than I hoped for. So that means that the overhead of our circuit is reasonable. So going forward, we can certainly improve this particular prototype, right? Shrink it, make it more like a product, make it much more efficient. But beyond that, really this same circuit can be applied to power different kinds of devices from different kinds of weak power sources. So here you see some examples, sensors for agriculture, maybe other implantable devices, or maybe small nanosatellites that you can launch into space. And the sources are diverse. It could be RF harvesting, it could be even a normal battery, but that's severely depleted. It could be a solar cell indoors. And finally, I want to thank very much the Michael and Linda Keston Endowment for funding this, and the ISI, in particular Arlington, for the shared lab. Thank you.
Alexei, very good work. But have you considered the case that you can take kinetic energy and transfer it to electrical energy?
Yeah, that's a great.
As the people move,
Absolutely.
kinetic energy can be transferred to electrical.
Exactly. Yes, harvesting mechanical energy in general is a big energy harvesting source. So the difficulty with harvesting mechanical energy is usually the best harvesters are the ones that can harvest vibrations. So it seems like there's so much movement, but this movement is actually hard to harvest much more efficiently. To harvest something more efficiently, you need like a vibrating source at a particular frequency to which you then tune your harvester resonator, and then you're able to generate, like, let's call it microwatts, so much more than this cell actually. So if you want to attach something to like an elbow, that will do well. But if you want to just put something like on your wrist and hope that it will charge like your watch might charge, that will work. But that's like, that might be even like tens of nanowatts. So it's tough, but I agree, harvesting body energy is really cool. There's also this thermal electric generator, which could give you somewhere between nanowatts and microwatts.